In this presentation, I'm going to be talking about how to write C for xcore targets. Specifically, I'll be showing how our new library, libxcore, allows the use of pure C, where before XC language support was required. This presentation is intended for developers who want to transition from using legacy XC code to C, so you'll need to be familiar with the C and XC languages and to have a good awareness of the hardware features of the xcore. First of all, why are we promoting the use of C over XC? XC enforces the creation of safe, predictable applications, but it does this by restricting the use of some C features. Using standard C means developers have full, unrestricted use of pointers and other C features. Of course, this isn't to say that the programming model enforced by XC is a bad one, but in C, where you want to break out of these patterns, for example for performance reasons, you can. The C language is also well specified and documented, meaning there's no ambiguity as to what a line of code means, and there's no need for developers to learn a new language to target the xcore. Finally, by using C, developers can benefit from the latest compilers and tools, and of course from the wealth of online knowledge and support. A key part of using C to target xcore tiles is libxcore. libxcore is a new C API for xcore hardware features which wouldn't otherwise be accessible using C. It provides low-level APIs for all xcore features which previously required the use of XC, as well as some which weren't previously available without using assembly, such as locks and interrupts. libxcore also provides preprocessor macro replacements for some XC concepts, such as select and par blocks, as well as compatibility headers for interacting with legacy XC applications, for example over channels. So let's take a look at how libxcore is used, starting with ports. As will be the case for many of these slides, on the left we've got some XC code, and on the right is how you'd write that same program in C. This is a trivial use of ports just to get started. libxcore is a system library whose headers all start xcore/. Most resources have a header, and most headers correspond to a single hardware feature or usage pattern. So in this case, we import xcore/port.h. One of the most significant changes when moving from XC to C is that resources no longer get special treatment by the language. In C, we use resource handles, which are ordinary variables which you can use just like you'd use a pointer. In XC, when using ports, we use a variable of the port type. The line shown here is quite different to a normal variable. For a start, it's only allowed to appear in certain places. That's because it has special semantics, and it'll make sure the physical port resource is enabled for us. In C, we use a port T from libxcore. This is an ordinary scalar type, so the line can appear anywhere any other variable can be declared, and nothing will stop us changing the port this variable refers to, or creating multiple handles to the same port. Most importantly, this line has no side effects, so creating this handle won't do anything to the physical port resource. Instead, we'll manage the port ourselves, which should be a more familiar experience for C programmers. The user must enable the port before it's first used and disable it when it's no longer required. The language also won't stop you sharing the port handle in ways which might be unsafe, so it's the programmer's responsibility to ensure that any sharing is safe. Of course, we can always follow the ordinary xcore programming model and restrict usage of our port to one task or place in the code, but if you want to do something clever, the option is there. We've not actually done anything useful with that port yet, just got it ready for use by the application. So let's look at how to add some I/O. In XC, we use the special input and output operators, but in C these aren't available. Instead, we use ordinary functions for I/O. The equivalent to the input operator for a port is the portin function, which takes the port handle and returns the value read from the port. Again, this should be a more familiar approach for C programmers. Following the same pattern, we use the portout function to output data using the port. Ports are extremely flexible, and libxcore has an extensive port API which exposes all of their functionality. Like with the basic I/O, all port operations are accessed using functions from the port header. In this case, I'm inverting the port and setting its trigger based on a peak operation. This will change the effect of subsequent input operations so that they're blocking. I'm not going to cover all of the features of ports, but you can check the port.h documentation to see the full range of port functions available. We've seen that it's possible to freely configure our resources using C, but with great power comes great responsibility. The C language doesn't keep track of the state of our ports. In fact, it doesn't know anything at all about the internal state of resources. So it's up to the application to ensure that the resources are in a suitable state when they're used. If we look at the previous example, we set a trigger on the port, which changed its behavior. If we pass that port to another function, it might not expect it to have a trigger. We could just call port reset to clear its configuration, but maybe our previous function should have cleared up after itself. There's no one-size-fits-all solution here, and you should consider a model you want to stick to when passing resources around. Moving on to another resource, timers. Like with ports, in the xc on the left we use a special timer type to declare a timer, which has special semantics. In C, we get timer-related names from xcore/hwtimer.h, and like with ports, we use a type from libxcore, in this case hwtimer_t. Unlike ports, timers are allocated from a pool by the xcore. We don't specify the particular timer we want. Instead, we call an alloc function to get a handle to a free timer, which also enables that timer. It's then our responsibility to free the timer when we're done with it. It disables the timer resource and returns it to the pool. You can think of this like malloc and free. We alloc the resource, use it for as long as we need it, and then we free it, but we don't use that handle before the allocation or after the free. Once we've allocated a timer, we can read its current value with hwtimer_getTime, which replaces xc's input operator for timers. libxcore gives you unrestricted access to the timer resource. The timer.h documentation details the full list of timer functions, but to give some examples of what's possible, you can set a trigger time so that input blocks until that time. You can read and modify an existing trigger. Here we use the hwtimer change trigger time function to set the trigger value without having to reconfigure the trigger type for a small speedup. There are also helper functions for using the timer to wait until a given timestamp, or wait a given number of ticks. A notable difference between timers in C and xc is that, by default, using a timer in xc usually doesn't give you exclusive use of a physical timer resource. Instead, in xc, each thread has a thread local timer, and all timers used in that thread share that physical thread local timer resource. This has a runtime overhead, but means you effectively have unlimited timers. You might have noticed the hardware timer attribute in the previous xc examples. This guarantees use of a dedicated hardware timer, and thus no runtime overhead. In C, all timers are as if declared this way. That is, libxcore hardware timers are always physical hardware timers, hence the name. The fact that each thread isn't given a thread local timer means that there are more hardware timers to go around, but if you still need software sharing of timers, you can implement a suitable scheme using libxcore. Next I'm going to talk a bit about locks. Locks aren't available in the xc language, but with unrestricted use of C features, you may find you want to use them. Xcore locks enable hardware-supported mutual exclusion and can be accessed using libxcore like other resources. You'll need to include xcore lock.h in order to use lock functions, and like timers, locks are allocated from a pool and freed when no longer needed. The API is pretty simple. Locks can only be acquired and released. Lock acquire blocks if the lock is held by another thread, and lock release releases the lock, which might unblock another thread if it's waiting for it. Notably, it's fine to acquire a lock your current thread already holds, but locks aren't recursive, so regardless of how many times you call acquire, you can only release once. Releasing a lock which isn't held by any thread will trap, but be careful, a thread can release a lock which it doesn't currently hold. This won't trap, and may result in another thread thinking it has a lock which it actually doesn't. Generally, you shouldn't make use of this, and should only release a lock you've previously acquired. Of course, locks aren't especially useful in a single-threaded application, which brings us on to parallelism, and specifically, libxcore's replacement for xc's par construct. libxcore's par replacement is provided as a set of macros which dispatch function calls in different threads. One style, the pjob style, allows dispatching functions with arbitrary parameter packs, but requires declaring these job functions upfront using a macro. The other style, pfuncs, dispatches void star functions, which don't require special declarations. Both styles act like xc's par in that all threads start simultaneously and must all finish before the block finishes, and both styles participate in stack size calculation and are implemented in terms of a low-level public threading API. Let's look at an example. Here on the left, we have a program which calls two simple functions in parallel, and on the right, we have the same application written using libxcore's pjob style par. Macros for par replacements come from the xcore parallel.h header. For a function to be dispatched by the pjob style par, it must be declared using the declareJob macro in the same translation unit where it's used. The arguments to the declareJob macro are the name of the function and a parameter type pack. The type pack must match the argument signature of the function with the names omitted, as in this example. There are some restrictions on the types which can appear here. CV qualification is fine, but arrays and pointer to function types are not allowed. Essentially, any type where the name appears in the middle of a declaration is not allowed. Once the functions are correctly declared, we can use them with the parjobs macro. Parjobs runs 2 or more pjobs. Each one will execute in a separate thread, but one will always execute in the current thread, meaning it's possible for one parjobs to dispatch functions to all available logical cores. This also means there's a hard limit on the number of pjobs appearing in a parjobs, which is the number of available logical cores. It's essential not to run more jobs than there are available logical cores, because that's a runtime error. Each argument to parjobs must be an expansion of the pjob macro. The arguments to the pjob macro are the name of the function to dispatch, followed by the arguments to call it with. You'll notice that the arguments to pjob look like a normal call, but with the function name and parameters separated by a comma. You might also have noticed that we never specified a return type for our job functions, and that's because all pjobs return void. This means that if you want to return a value from a pjob, you'll need to do so through a pointer parameter, like in this example. Whilst this is different to XC, it's got clear semantics and it's not restricted by XC's thread disjointness rules. As a slight special case, if you want to launch a job that has no arguments, you can do so like any other function. However, the parameter pack passed to declare job must contain only one type, which must be exactly void as shown. You'll also still need to specify an empty parameter pack to pjob, like with a normal function call. Internally, this style of par creates an argument struct and helper shim to marshal arguments between threads. If you don't want this support, you can use the alternative pfunc style. Macros for the pfunc style are available from the same header as pjobs, xcore parallel.h. This style only dispatches functions with a void star signature, but has the advantage that it doesn't require declaring job functions up front. It's also sometimes possible to get slightly better performance from this style, especially where a sole pointer argument is the natural signature for the function. To use this style of parallelism, we use the parfuncs macro. Each of its arguments must be an expansion of the pfunc macro, whose arguments are the name of the function, followed by the value to use for its pointer argument, which must be implicitly convertible to a void pointer. As you can see, this style can require additional code to handle parameters manually. A major feature of xcore and the XC language is channels. These are supported by libxcore, and libxcore channels are compatible with XC channels, which enables integration with legacy XC code. Functions for regular channels, as declared using the chan keyword in XC, are in xcore channel.h. Channels are allocated using chanalloc and freed with chanFree. Unlike in XC, channels won't decay into chanends when passed to functions expecting a chanend. Instead, we choose which end of the channel to pass from the end A and end B members of the channel we allocated. As with other resources, functions replace XC's IO operators for channels. Here we use chanoutWord to send an integer, and we can choose between sending words and sending bytes. This requires some care. Because we specify manually how many bits to send and receive, it's possible to accidentally introduce a mismatch. It's essential that the receiving end reads the same width of value from the channel which was sent. For example, if we send a word down a channel, the receiving end must read a word. If instead it tries to read a byte, this will cause unpredictable behavior, probably ultimately leading to a lockup or a trap. In addition to sending words and bytes, we can also send and receive arrays of either. But as before, it's imperative to ensure that the corresponding receive function is used for the send function, and that the array lengths sent and received match. Using the array IO functions can perform better than iterating over arrays sending single values. libxcore also has streaming channels compatible with XCs. The streaming channel API is under xcore/channelstreaming.h. It's much the same as the regular channel header, except function names are prefixed with s_, and those functions operate on a streaming channel T rather than a channel T. Beware that channels and streaming channels are not compatible, so it's not safe to send data using a standard channel function but receive it using a streaming version. Streaming channels offer generally better performance than regular channels, by not synchronizing on each send and receive pair. It's important to remember that this means the physical route through the network stays open, which may starve other channels, streaming or otherwise, of network capacity. So streaming channels should generally be allocated only when needed and freed as soon as they're no longer required. Moving on to another major XC feature, libxcore provides a replacement for select blocks. Like par, the select replacement is exposed as a set of macros. The replacement supports all the basic features of XC select: default cases, guarded cases including guarded defaults, and ordered selects. Unlike XCs, libxcore selects work on generic resources. That is, they offer no special behavior which would depend on the actual type of resource producing events. For example, a libxcore select won't reconfigure your timer after an event. For unusual cases where a select is too prescriptive, there's a lower level API available in libxcore, but I won't be covering that in these slides. Looking at some code, on the left we have a simple XC select which handles a timer event. In the C version, we start by including the xcore select.h header, which provides the select macros. You can see that these macros enable a style similar to that of an XC select. The structure is similar, but unlike an XC, we have to provide all the cases we're selecting on as arguments to the select res macro. In this case, we're specifying that when an event occurs on our timer t, we should jump to the label timer handler. As we are responsible for the resource-specific behavior, you'll notice that we configure and read our timer manually. We configured the timer trigger outside the select block and read its value manually at the start of our handler. Note that it's essential that you read from a resource in its handler by calling an appropriate input function on it. Now this select only runs once, but most of the time we want to handle several events sequentially. libxcore selects are always loops, so in our example we can just replace the break with a continue to go back and handle another event. Because we are responsible for configuring our resources though, we have to update the timer's trigger condition so that it's in the future again. We can add a default case using the default then macro. This will move control to the default handler label if no relevant events are available on entry to the select block. Cases can be guarded like an XC. Here we use case guard then in the place of case then to specify a condition. An nguard variant is also available, which simply inverts the condition as if using a bang. Here, if an event is available on T when we enter the select, it'll only be taken if our default last flag is non-zero. There are guard and nguard variants of select default too, which work the same way. If the guard condition isn't satisfied on entry to the select, it's as if there were no default at all, so we'll wait for an event if there isn't one available. There's also an equivalent to XC's ordered attribute. To get an ordered select, replace select res with select res ordered. Like an XC, this is similar to an ordinary select block, but cases specified earlier in the list are given preference when selecting an event to handle. In this trivial example, it has no functional effect. In general, it can be used to make sure high priority events are serviced in preference to lower priority ones, but can incur a slight slowdown on each entry to and continuation of the select compared to an unordered one. It's worth being aware that a select block modifies the thread's global state on entry, and it doesn't restore it when it finishes. This means that when selects are nested, the outer select needs to rerun its global setup when an inner one completes if it's going to handle another event, like when the outer handler ends in continue. The select construct takes care of this, and will rerun the global setup if required when a continue is reached. However, it uses a runtime check to achieve this, which naturally has a small performance penalty. We can guide this behavior by using one of two macros in the place of continue. We can use the select continue reset macro if we know that a handler has run an inner select, so we need to rerun global setup, or if it's very likely. This allows us to skip the runtime check and unconditionally reinitialize the select. If we know we definitely haven't run an inner select, we can use select continue no reset to unconditionally skip the reinitialization. Note that if this is used incorrectly, where an inner select has run, the select will behave unpredictably. A reasonable approach is to only use this where the handler is trivial and doesn't call out to other application code. The reinitialization cost is relatively small. It varies with the complexity of the select and is of the order of a couple of cycles per case. For this reason, using a normal continue is often a good default, but these macros can be useful in cases where performance really matters. We've now looked at most of the key features of libxcore, but there are other features and headers available. I'm going to quickly talk about some particularly interesting ones now. If you want more information, have a look at the libxcore documentation, which discusses these and other features in more depth. First of all, assertions. The xcore assert.h header contains assertions which, by default, use the xcore's hardware assert instructions. Xassert is equivalent to the C standard library's assert, and with assertions enabled, it'll trap when its argument is 0. There's also an inverted version, xassert not, which traps on a non-zero argument. This is functionally equivalent to negating the argument to a normal assert, but can result in better instruction selection in some cases. The effect of assertions can be configured by defining certain macros. By default, assertions are effective and use the xcore assert instructions for a low overhead assertion. If you define libxcore xassert is assert, then xasserts expand to the standard library assertions. And, like the standard library assert, if you define ndebug, the assert is ineffective and pre-processed out. Naturally, this means that assert arguments should be non-side affecting, again, like a standard assert. libxcore also has a low-level threading API under xcore thread-h. With this model, all launched threads are functions with a void star signature, and unlike with the par macros, when using the low-level thread API, the user must provide appropriate stacks for threads. The stack base helper can be used to compute a stack pointer given a suitably aligned base and size. The simplest way of launching a function in another thread is by using the run async function. This sets the function running but returns no handle, so it's not trivially possible to know if it's finished. This also means it's not possible to know that the logical core has been freed and made available for further use. This is mainly useful if you just want to launch a service which never finishes. For other cases, the xthread style provides a familiar interface for C programmers. Here, we use xthread allocant start to launch our thread. This allocates a thread resource and starts it running with the given function, parameter, and stack. The return value is a handle to the thread, which we can then use to wait for the thread to complete using xthread wait and free, which also frees the logical core. A third style is available for use where you want to launch and wait for a group of related threads. Thread groups let you keep track of such a group with a single handle. Here, we allocate a new group with thread group alloc. We add threads to the group with thread group add. This takes the group plus the same function, parameter, and stack as an xthread. We then start all the threads running simultaneously using thread group start. And finally, we use thread group wait and free to wait until all the threads in the group are finished. This will also free the associated resources. libxcore offers several low-level headers which can be used where existing patterns aren't suitable. Another such header is the low-level chanend API, which gives access to the chanend resources which underpin channels. As with other resources, we can allocate and free individual channel ends. We can also configure and retrieve their destination ends. All features of channel ends are exposed through functions in this header, so it's possible to implement new schemes for inter-thread communication. For example, you can send and check control tokens, read and write bytes and words, test for the presence of buffered control tokens, and easily check whether the remote chanend is local to the tile and thus has a common view of memory. Generally speaking, the higher level channel headers should be used. They're flexible enough for most applications. Implementing new channel protocols can be complicated due to network topology considerations. Another xcore feature newly exposed by libxcore is interrupts. The interrupt API is split over multiple headers. Functions for controlling the global interrupt state are in xcore/interrupt.h. Macros for implementing interruptible functions and interrupt handlers in xcore interrupt wrappers.h. And triggerable.h provides functions for configuring resources to generate interrupts. We can create an interrupt handler using the define interrupt callback macro. Its first argument is a group name used for stack size calculation. It should be an otherwise unused name and will be used to calculate the worst case stack footprint of handling an interrupt. The second argument is a name for the interrupt handler. This is essentially a function name used to retrieve the handler later, so it must be a valid, unique name. The final argument is the name used for a void star argument which is passed to the interrupt handler implicitly. Here we use the argument to pass in the resource which raised the interrupt, but we can set this to an arbitrary value. Define interrupt permitted is used to define an interruptible function. It makes sure we allocate enough stack that the function can be interrupted at any point and call the hungriest possible interrupt handler. Its first parameter is the group name. This must be the same group name which was used with define interrupt callback when defining all possible handlers which we might call. The remaining arguments set the signature of the function being defined, the first being the return type, the second a base name, and all remaining arguments being used as the parameter signature, meaning this can be used to add arguments to the function if required. Interrupts are not automatically enabled within this function. Instead, they should be enabled and disabled manually using interrupt unmask all and interrupt mask all respectively. We now just need to configure our resources to raise interrupts before we can call our interruptible function. To do this, we use triggerable setup interrupt callback. This takes a resource handler as its first parameter, the resource which will raise interrupts when triggered. In this case, we use a button. The final parameter is the interrupt handler to use. We retrieve the handler we defined earlier using interrupt callback, plus the base name we assigned it. The second argument is used as the void star argument to our handler. Here, we pass a pointer to our button handle, so we can reuse the interrupt handler, but this can be any pointer. We now set a trigger on the port to set the condition under which an interrupt will be raised. The functions to use here vary by use case and resource. We can now enable the trigger on our resource so that it can start raising interrupts. Note that these interrupts will have no effect unless we've reached the point in our handler where we unmask interrupts. And finally, we retrieve our interruptible function using interrupt permitted and call it. Because we declared it with no arguments, we pass an empty argument pack. I've now covered many of the features of libxcore, so it's a good time to take a look at a couple of considerations when using it. First of all, throughout these slides, we've called allocation functions and trusted that they return valid resources. However, as I said previously, you can think of libxcore allocation in the same way as a standard library malloc, and this includes checking of return values. libxcore allocation functions can fail if there are no free resources of the requested type. In this case, they'll return a zero handle, or both ends will be zero in the case of channels. Usually, left unchecked, a subsequent operation will trap on a zero handle. You should consider what checking is appropriate for your application. Often, it's appropriate to check all allocations were successful before using their return value by simply checking them on zero, or you can assert on the returned handles. Another thing to be aware of is optimization. Where XC natively supported certain features, we now use function calls in C. With low or no optimization, this can produce larger and slower code than XC did for an equivalent application. However, libxcore is highly optimizable, and nearly all functions can be inlined. You can see how the size and number of calls in the code drops as the optimization level increases. At high optimization levels, libxcore-based code compiled with modern Clang can outperform equivalent XC code. You might notice that the code size actually increased a bit at 03 there. This is due to a speed enhancement in our select, which is beyond the scope of this presentation. So how do you get libxcore? Well, it's actually already included with the latest tools. It's a system library with its headers automatically available and code automatically linked. With the latest tools, the examples in these slides will compile and run out of the box. We're continuously expanding the API, and will consider enhancements to overcome any limitations, issues, or missing features. And there are some known limitations when using C in libxcore. First, there's no replacement for XC's combinable attribute, so select blocks must be composed manually. Non-memory resource calculation is not supported. When producing a resource report, only memory will be included. And XC-style interfaces aren't supported, so explicit channels should be used to define inter-task communications. Documentation for libxcore is of course available. The API is fully Doxygen annotated, and additionally these slides are available. Further information about programming xcore tiles using C is included with the tools. That concludes the libxcore section, but there are a couple of other important topics to cover. First of all, automatic stack size calculation. A common approach to assigning stacks is to put aside a block of memory at link time, which is sized to be more than enough for the application. Xcore applications usually have several threads, and often there are many short-lived worker threads, given the speed and ease of launching them. This means that calculating and assigning stacks can be complicated. So to simplify this, the xcore tools attempt to calculate the maximum stack size required for an application automatically. When using XC, this is almost always possible, due to the language restrictions, but when using C, there are cases where the tools can't deduce the worst case stack requirement automatically. Most commonly, this happens when function pointers are used, because the compiler can't know which function will ultimately be called. For this reason, indirect call sites and their potential callees must be annotated to enable the calculations to succeed. In this example, we make a couple of simple indirect calls which land at our two compatible functions. But because the code is unannotated, the compiler can't deduce the required stack size. It'll warn about the calls which haven't been annotated, and the linker won't know how much memory to assign to the stack, so the stack it does assign is likely to be insufficient. This will often be a link time error. In order to get correct calculations, we need to tell the compiler which functions our pointer might refer to. To do this, we annotate the relevant code. We assign a group to the function pointer. Here we see that our pointer fp refers to a function in the group myFunctions. We also need to annotate each possible callee to say that it belongs to that group. We apply the same attribute as before to all possible callee functions. The stack required for this application is now calculable, and xmap will assign enough stack space for both our indirect calls. It's important to be careful when annotating code, as mistakes generally can't be detected by the tools. Here, setting an incorrect group on our function will prevent the tools considering it a possible callee for stack size calculation purposes. This is likely to result in an insufficient stack being allocated, and as we see here, there's no diagnostic even though our group was never used. It's possible to enable runtime checking of indirect calls, and we do this by passing the second argument to the attribute on our function pointer. Calls through this pointer will now be checked at runtime, and if the pointer refers to a function which is not in the correct group, a trap will be raised. This means that this sort of mistake would cause a trap, as we can see here when we run our application. Note that runtime checking is relatively expensive, it should be used sparingly, and might not be appropriate for release code. Where it's not possible or desirable to annotate source code, it's also possible to provide the stack size requirements by hand at a function level. Again, this requires care, as it can't be verified by the tools, and assigned sizes must be sufficient for all callees and spawned threads of a function. In this case, we set the stack size for our main function to 1024 words. We can do this for any non-static function. We can use simple expressions and refer to other symbols. Here, we add another function's requirement, which is useful when we want to allocate enough stack for a function's callees. We can use the m operator to find the greater of two operands, which is useful for finding the hungriest of a function's callees. It's also our responsibility to make sure the stack is a multiple of its alignment requirement. We can use the a operator for this, which rounds its left-hand argument up to a multiple of the right-hand argument. You can provide this to the tools at build time, but you might still see warnings about unannotated code if it's incalculable. You can silence the warnings with the wno xcore fpointer group option. You can see here that the linker has produced an OK rather than a maybe for stack size, since we've provided it manually. So far in this presentation, I've only talked about code which targets a single xcore tile. In fact, this is because C cannot target multiple tiles, as they're essentially unrelated processes. So in order to target multiple tiles, we need something to orchestrate running multiple single-tile C applications. In the future, we'll provide a code generator tool driven by a declarative application definition. But for now, we can use xc to launch our tile applications. It's advisable to future-proof applications by using a single xc file to launch C code, and ensuring this contains only the bare minimum xc for that purpose. Simply, xc should not be used for procedural code. This is an example of a minimal xc file which launches two tile-level applications which communicate using a channel. We forward declare our C entry point functions using the xc counterparts of any resource types. We declare our channel within the main function. This single channel can be used by our tile-level applications to bootstrap further into tile channels if they're required. Finally, we launch the two tile-level tasks using a par block. Notice that this code is essentially declarative and no application logic is captured in the file. That concludes this presentation on programming xcore tiles using C and libxcore. If you want more information on the topics discussed, check out the documentation included with the latest tools.